Alright, let's get live. Are we going live? Looks like we are. Okay, so we are going to be working on some neural network classification problems with PyTorch. Now, if you're not sure about PyTorch or about neural network classification, that is fine. We're going to code this all from scratch, and all of the materials that you need are at learnpytorch.io. So I'll put this in the chat. Otherwise, just go to learnpytorch.io. We are working on notebook number 2. And if you have zero experience with PyTorch and whatnot, I would suggest going through 000102. But let's start with 02. Now, this is all the materials, the backing materials that we're going to be working through. But down the bottom of this, so this is a course that I'm working on to learn PyTorch. It's still a work in progress, but right now I've done 3 modules, almost to completion. You'll see the TKs so far on learnpytorch.io. If you're in the future, you're probably not going to see the TKs because it's finished. TK just means that I need to finish it. But yeah, there's a GitHub for it as well, PyTorch Deep Learning, Mr. D. Burke / PyTorch Deep Learning. There's going to be about 8 notebooks by the time that it's finished to start right from the beginning all the way up to a few milestone projects with PyTorch. But now let's, I'm going to put this stuff over here so that I don't mess anything up. If you're joining in, say hello in the chat and let me know if you can't hear or can't see anything. But without any further ado, let's get started. So I've got all the code here. So this notebook gets built into this like online book. Then we've got all the headings here. So we're going to be working through a PyTorch workflow. So step 1, get data ready, turn it into tensors. Step 2, build or pick a tree-trained model to suit your problem. 2.1, pick a loss function and optimizer. A loss function measures how wrong your model is. So if you're trying to predict something, remember classification, I haven't actually said this, so why am I saying remember? Classification is predicting whether something is one thing or another. Say, for example, you had a photo of a dog and a photo of a cat. You want to classify which photo is which. Which one's a dog, which one's a cat. Or if you had an email and you want to classify which one's spam and not spam. So a loss function measures how wrong your model is. So if a loss is high, it means your model is quite wrong. If it's low, it means that your model is doing quite well. Build a training loop. So that means a training loop takes steps over your data. We're going to see all this in code in a second. So as in, you start with your data set here. Say it's photos of cats and dogs. Your training loop will iterate over your data. So go through each of those photos and allow your model to make predictions on whether those images are a cat or dog. The loss function measures how wrong those predictions are. And then the optimizer does what its name says. It optimizes your model, so it pushes your model in the right direction of predicting the right prediction of cat or dog. We fit the model to make a prediction, so go over the training data. We evaluate it. We can improve through experimentation. Lots of things you could do here. And then we save and reload the trained model. But now, let's get into the exercises. So down here, you can, if you're looking at learnpytorch.io, you can go to the exercises, and this is what we're going to be working through. All exercises should be completed using device agnostic code. What does that mean? Doesn't matter. Let's just start going through them. I've got a Google Collab notebook here, which I'm assuming that you can see, but if not, I'll move my head. I'm just watching the stream to see if you can see this. I just had to adjust my pants as well. But let's get started. I'll zoom right in. It should be enough. Okay, so Google Colab is the easiest way to get started with this notebook. You can run them locally. However, there's a button right up the top of these that you can just go open in Google Colab. So that's what I've done here. You can click open in Google Colab, start a new notebook. And Google Colab is a notebook that's going to give us access to writing Python code in an interactive way. Alex, what's going on? Nice to see you. If you're watching this in the future, this originally is a live stream. So what I'm going to do is I'm going to use a GPU. So hardware accelerator, GPU. That's going to make all my code run faster. If you don't have a GPU on your local machine, Google Collab does that for you. So exercise solutions. So all exercises should be completed using device agnostic code. What does that mean? So in PyTorch, you have to decide where your data and model live. So by default, everything starts on the CPU. The CPU is computer processing unit. The CPU is not as fast as the GPU for performing certain numerical calculations. At the end of the day, that's what a neural network does. It performs a series of numerical calculations on data, which is in the form of tensors. And if you'd like that, those calculations to be done faster, you should use a GPU. So we have access to a GPU. Let's check for a GPU. So NVIDIA SMI. You've been slacking on the DB streams. Hey, that's fine. I've been slacking on doing the streams, but I'm going to get straight back into it. So I got access to a NVIDIA GPU powered by Cuda, which is excellent. And then we're going to now do base imports. So we're going to import Torch, because this is the exercise we're going to work through. Make a binary classification dataset with scikit-learn's make moon function. So let's see what that is. Oh, I actually don't want that there. I want it over here. Import Torch. And we're going to set up device agnostic code here. So device equals Cuda if torch Cuda.is available. Now, if you're not sure what Cuda is, else CPU. So then we can check what the device is. Invalid syntax. Oh, I spelled else wrong. What is Cuda? So Cuda is parallel programming for GPUs. I think that's a good enough summary for me. What is Cuda? So NVIDIA is basically the #1 GPU company, and their programming system is called Cuda. And if you want to use their GPUs, you basically have to write Cuda code. PyTorch takes care of all that for us. So we can write Python or PyTorch. Pi in PyTorch stands for Python. And we can leverage Cuda. So this is going to set up device agnostic code. Device equals Cuda, which is NVIDIA's programming language for GPUs, if torch.cuda, which is PyTorch's Cuda module, is available. Else, CPU. And see, because we have activated a GPU by going runtime, change runtime type GPU, we have Cuda available. Now, let's go on to exercise number 1. Make a binary classification dataset with scikit-learn's make moon function. I like this. 1. We'll turn this into Markdown. And then I'll go here. I might copy the exercises in here from the original notebook. I think this is a good idea. That way I'll have the links and the code formatting and everything like that. That'll look much better. There we go. Okay, so now let's jump into the make moons function and see what we can do. Is there example usage? Not really. The data set should have 1,000 samples, so we should write here num samples equals 1,000, random seed equals 42. We can use these all later on. And let's create it. So x, y equals, we'll need scikit-learn. So import sklearn. And we could just import from sklearn.datasets. We'll import make moons. Excellent. And then we have a simple interface to make some classification data here. We're going to see what this looks like in a minute. make moons and n samples equals num samples. And then we can go random state equals random seed. We're using 42. So the random seed, what's that going to do? The random seed, so computers use pseudo randomness to generate numbers. So if you tell a computer to generate random numbers, because a computer is deterministic, it's actually pseudo randomness, and I'll let you look that up. The random seed flavors our computer's randomness. So that means if we were to run this same function again, we would get the same amount, the same different random points. And this is going to be confusing unless we look at it. So let's do that. I'm going to introduce a little bit of noise. I think 0.03 might be enough, but we'll find out. Now, let's just have a look at what x and y look like. Maybe the first 10 samples of each, because we have 1,000 of each due to the n samples parameter. Okay, wonderful. So we have an array of x values here and an array of y values here. So x has 2 features. So this is 1, 2. Now, what happens if we turn this into a data frame? So let's go df, data df, turn data into a data frame. We can visualize it this way. Import pandas as PD, and data df is going to be PD data frame. And we want a dictionary. We'll put x1 or x0 is equal to x and everything on the zeroth column. And then we'll go x1, which is x feature 1, is going to be everything on the first index column. And then we'll go y for label equals y. What's this look like? Okay, beautiful. So we have x, y, x0, x1, y. These are 2 features which lead to this label. So we have a supervised learning problem, and we're working with binary classification. How do we know that it's binary classification? So this is make a binary classification. We only have 0s and 1s. So that means our x features could be 0 or they could be 1. Binary classification means 1 or the other. 2 options. And so now let's visualize the data on a plot. So we want import matplotlib.pyplot as plt.plot. What happens if we just go xy? What will that do? Okay, all over the place. I think we need to go x0, plot that first, and then plt.plot x1 first. I don't actually know if this will work. No, that's just the exact same thing that we got before. Okay, I think I know what to do. We need to go x01, then we need to color it with y. RBGA should have a length 3 or 4. Now, this is where I need to go back to my own code and reference it. So all of these exercises are based off what we did here. What have we got wrong here? Oh, scatter. We want a scatter plot. There we go. We've got 2 moons, and let's color these to be red and blue dots. So this is just taking from, this is where the exercises are based off, right? That's the point of code. The point of writing code, of course, is not to repeat the same code that you write over and over again. It's to write it once and then reference back to it if you need to. So we're referencing back to the code that we previously wrote. CMap equals plt.cm, red, yellow, blue. That just means, okay, maybe we increase the noise a little bit. I think I'd like more noise. So noise equals 7. Yeah, there we go. Okay, so now this is what we're trying to do. We're trying to build a model that's going to separate the blue and red dots. And you might think that this is very trivial, Daniel. They're already separate. And yes, you would be 100% correct in saying that. They are already separate. But how about we build a model that can draw a line through here? So separating them like the curves that they are. Well, let's give it a shot. We'll go back to the exercises. What are we up to? I want you to have a think about this actually before we build a model, is can this be separated by a straight line? This is a very important point in neural networks actually, by the way. Can you draw a straight line to separate these two red and blue dots? Just think about that. We'll come back to that in a second. So number 2 is, let's go into here. Build a model by subclassing NN module that incorporates nonlinear activation functions and is capable of fitting data capable of fitting the data you created in one. Feel free to use any combination of PyTorch layers, linear and nonlinear. Ah, there's a little hint there. Okay, first of all, we need to discuss what linear is. So linear is a straight line. Let's create this. Have we got torch? If not, we'll just get it again. Linear line equals torch dot a range 0 to 100 and the step is 1, and then plt dot plot linear line. Right, that's linear. Linear means straight, and then non-linear means not straight. So let's do a little. We'll use an activation function, a nonlinear activation function. Or maybe we go, this can be a bit better. -100 to 1. Close, that's all right. We don't need that. I'm just discussing the difference between linear and nonlinear here. So could this straight line, if we built a model to predict, to separate, a model to separate these two data sources, can it do it with a straight line? I mean, it would do most of them, but not all of them. So that's a problem. You might have seen this line of best fit used somewhere before, like in high school mathematics. But we need something that has some curves in it, don't we? Now, how can we get some curves? Well, that's when we bring in nonlinearity. So if we go use a nonlinear activation function like torch sigmoid on the linear line, what does this look like? Oh yeah, we got some curves. Look at that. Now, what if we used ReLU? Now, I've just thrown a lot of information at you to begin with, but essentially the whole crux of neural networks is combining linear straight line functions and non-linear non-straight line functions together to model some kind of data. Now, our data set is quite simple. There's only 2 features, x0 and x1. But what if you had x0 to 10,000? How do you model that? In the same process, you combine lots of straight and lots of non-linear lines. The question is, what could you draw if you had an unlimited amount of straight and non-straight lines? You could draw a pretty intricate pattern, couldn't you? Well, let's see it in action, hey? So, what do we got here? Build a model by subclassing NN module that incorporates nonlinear activation functions and is capable of fitting the data you create in one. So, actually, we've missed 2 steps up here. Split the data into PyTorch tensors, or turn the data. So, let's do that, and then we'll split it into... So, turn data into tensors. So we have x equals torch tensor x, and we're going to set d type equals torch.float. Torch.float is float32, which is the default data type in PyTorch, which is more than enough for us now. There are other data types, but I'll let you dig into them. And let's split the data. into train and test sets. Why do we do this? Well, think of it like you're taking an exam. If we want our model to be able to learn things in the real world, we don't want it to, we need some portion of the data that we can evaluate it. So instead of just building a model in a notebook that works really well on these blue and red dots, what if we had someone who was just wanted to randomly give us some blue and red dots? How could we evaluate how our model would go on those? Well, we kind of pseudo evaluate it. I say pseudo. What's a better word? I can't think of the right word. But a training set is like the course materials that you take before you take the final exam. You wouldn't really be testing your knowledge if you could see the final exam before you took it. So when we build our model, we train it on the training data, and then we evaluate it on the testing data, just like when you learn the course materials, and then you test your knowledge on the final exam. Let's go train split. We'll use 80-20. So 80% of the data will be used for training and 20% of the data will be used for testing, equals int 0.8, so 80% times length of x, and I think that should be enough. What does that look like? 800. Okay, beautiful. So then we want to go, oh, we could actually just do random. Let's do that. So from sklearn.modelSelection, import train test split. And you're like, Daniel, why are we just doing blue and red dots? Well, because we're just learning the principles of a PyTorch workflow. So let's go back up here. This is what we're learning. Just the workflow. You can adjust this workflow to any data set you're using later on. Xtrain, Xtest. That's actually a very good way to start with machine learning concepts, is to start with a small data set first and then use a larger data set later on. So test size is 20%, and the random state here is going to be equal to the random seed. Wonderful. So this should give us an 80-20 split. Random split, that is, but using a random seed. Xtest. Let's go ytrain and len ytest. It should be 800, 800, 200, 200. Okay. Clone. Okay. Oh, there were already tensors. So the only reason that happened is because we got a clone warning, but that's because they were already tensors. Okay, beautiful. Yo, Ashik, what's going on, my friend? There we go. So we have 800 training samples, 200 testing samples, 800 training labels, and 200 testing labels. Hey, Ashik, thank you for the subscription, my friend. Now we have a data set. Let's get rid of this. We have training and test data. Let's go back to the exercises. So let's build a model. I'm just going to start right from the top. Import torch. Every time I'm going to just import things, even though we don't need to write this every time, but I'm going to do it so you get some familiarity with doing it. So we're going to create a class because we want to model our moon data. Let's call it moon model. Maybe moon model v0 because it's the first one. We might build a few models here, I don't know. And then module. So when you're creating a class in Python, you can create it just without inheriting from anything. So class moon model and start it off from there. But you can also create it by inheriting from something. So this means, hey, my class moon model is going to get all of the functionality of nn.module. And nn.module in PyTorch, basically everything in neural networks or everything in PyTorch neural networks inherits from NN module. So you can think of NN module as Lego bricks for neural networks. If we're constructing a neural network, we want all of the functionality that NN module provides. Hence why our moon model, our classification neural network, inherits from it. And then this is a bit confusing if you've never written much Python classes before. You have to write like a def, a init function, and you have to write like super init like that. I'll let you look into like what that actually means, but just get used to writing. If you're inheriting from NN module, you're gonna have like this boilerplate code to begin with. So let's go. You can also put the name of the class here, but you don't actually have to. Self. So you don't need that there. You can if you want, you don't need that there. So this just means, hey, initialize Mu model v0 class and inherit from NN module, and then initialize these upcoming variables. So we're not going to copy what's going on here. Let's just go back there. And do we need any? I think we can get away with just creating some layers. So self dot linear layers. Let's go self dot linear 1 equals nn dot linear. So this is going to be a linear layer in PyTorch. I'll show you what that is in a second. In features. How many in features do we want? That could be a parameter. In features. We want out features as well. And let's go hidden units. So in features can be in features. Out features can be out features. And we want self.linear2 can be nn.linear. In features. Now what is this going to have to be? In features equals, so we need to line these up. So the in features here, actually the out features are going to be a little bit confusing. I need a demonstration of this, what this looks like. TensorFlow Playground. When you're constructing neural networks, baseline neural networks, if this one outputs 2 features, 2 here, the input features, it's not pictured very well here, to these 4 neurons has to be 2 as well. Then this is going to output 4 features. The input features to this layer have to be 4. Then this can output whatever it wants. So let me just code this up and I'll explain it in a second. So in features equals hidden units. Because why? We're taking the output features, the size of the output features, which is hidden units, as the in features to the next layer. And then we can go out features. This one can be hidden units. And then we got, let's do another third linear layer. Self.linear3. And then .linear in features equals hidden units. And then out features equals out features. Okay, so we've got 3 linear layers. Now what is a linear layer? Let's go torch and then linear. Again, all of this is covered in materials here. We're just going to briefly overview. So the linear applies a linear transformation to the incoming data. Y equals x times a, which is the weight tensor, which is transpose plus a bias. This is the same as the line of best fit. Y equals mx plus c. Look at that. It's basically the same. Where c is the bias. You ever done a line of best fit? There we go. Y equals mx plus c. This is the linear function in PyTorch. So, question is, if we combine 3 straight line functions, can we model our data? What did we discuss before? This is curvy data. So will 3 straight line functions, linear, be able to model the data? I don't know. Let's find out. Then we're going to create a forward method here, which inherits from self. A little bit confusing if you've never done PyTorch classes, but just means, hey, this forward method belongs to this class. And we're going to take x as an input, which is, you can actually put whatever you want here. you can put input, but X is kind of universal across different PyTorch examples that you're going to find. And then the forward, what does the forward method do? When you define a subclass of NN module, the forward method, let's look it up, defines the computation performed at every call, should be overwritten by all subclasses. That means if you subclass from NN module from PyTorch, remember NN module is like Lego bricks for PyTorch models. You combine everything from different NN modules to create your PyTorch neural networks, plus a few other things, but NN module is your number one. The forward method defines the forward computation of your neural network. So if we just look this up, neural network, right? A forward computation just means you put your inputs through these two nodes, and then they get calculated on these hidden layers, and then they get outputted here. So look what we've got here. We've got linear 1, which is the input. We've got linear 2, which you could classify as the hidden, hence why I've got hidden units. And then we've got linear 3, which is the out feature. And in features and out features are just parameters of the linear layer. A lot to cover here, but let's see what happens. So we could do this. I'll show you two ways of doing it. X equals self.linear1. We could do this all sequentially, just like this. Linear, oh, did I do linear 1? No, linear 2, x. And then x equals self.linear3. And then return x. So that's progressively putting x through all three layers at once. Or you can do it like this, self.linear3 on the inside of self.linear2, on the inside, or outside, sorry, of linear 1, and then x is in there. So generally, you're going to see, it might seem like they're doing the exact computation, but you're going to see speed ups if you can do your computations like this. So these are like linking them all together in one hit, rather than reassigning x for 3 different steps. It shouldn't matter too much with our small model here, but depending on what type of computations you're performing, this is generally a good speed up. So let's see here, return x. Invalid syntax. Where's my mistake? Oh, I need an extra bracket. There we go. So now if we look up, let's set it to moon model, or we'll call it model 0, just so we're writing less code. Model 0 equals moon model v1. v0, and the in features is going to be the number of features our data has, which is 2. Why 2? Because we have x0 and x1. So these are the 2 features, 1, 2. That would change. If we had x all the way up to 10, we would put in features is 10. Hidden units. This is for our neural network. If we want 7 hidden units, it will be like that. And if we want 4 hidden units, it will be like that. So let's do that. Out features equals 4. If anyone knows a good PyTorch visualization software, I'd like to use that. And then, oh sorry, that was hidden units. Hidden units equals 4. And then what is our out features? Well, our out features equals 1. Why? Because we want our model to predict 0 or 1. Or could it be 2? It could be 2, but I'm going to go with 1 for the time being. We'll see later on. We'll find out. And then we're going to write a little bit of code here, to.device. What does this do? Well, what did we set the device as before? So remember, we're writing device agnostic code. So our device is Cuda. So what this is going to do is create moon model v0 using what we've just created here. And then it's going to send it to the target device. You'll see this throughout PyTorch a lot, .to device, or something similar to this. Device is pretty universal around all the examples you'll find. And this just means, hey, put our model on the GPU, which is Cuda. Or if we just left it like that, by default, our model would be on the CPU. But because we've written device agnostic code, if a GPU is available, it will be set to the device. If it's not, by default, this device will be set to CPU and it will go to the CPU. Let's have a look. In featurers, of course, we've got a typo. This is just sending it to the device. Yeah, Ashik is saying in the chat, when we stack linear layers on top of each other, all the weights from each layer combines into a single weight variable. Yeah, well, that's what we've done here. We're going to see in a second, what do you think is going to happen if you combine 3 straight line functions, 3 linear functions on top of each other? So now we've got our model on the device. What was the next exercise? Okay, we've got that. We're up to exercise 3. Here we go. Now, this exercise is termed pretty straight up. Set up a binary classification compatible loss function and optimize it to use when training the model. The model is model built into. I'm going to write this. Built into. So when it comes to loss functions, let's have a look at the, let's go, oops. Loss function. We'll go to the architecture. So remember, these exercises are based off the Learn PyTorch.io number 2. So you would have already gone through this section here, architecture of a classification neural network. Because we're using binary classification, our loss function is going to be binary cross entropy. Now, there are many different types of loss functions, but for binary classification, generally you're going to find torch.nn/BCE loss. If you want to look up the function for that, binary cross entropy, there we go. You'll find articles galore on how to use that. Because we're focused on code, we're just going to focus on coding it out. And then the optimizer, a very common optimizer to use is stochastic gradient descent or Atom, but torch.optim has a bunch of different optimizers ready to go as well. But again, by far the most common ones are stochastic gradient descent and Atom. A few variants of Atom that are quite popular recently, but those two are the most popular. So let's see how we can do this. And by the way, this is where we're up to. We're still going through the workflow. Get the data ready. Well, we've done that. We've got the data ready. It's in training and test sets. Build a model. Well, we've built a model here. And again, this model will differ depending on what problem you're working on. And now we're up to 2.1. Pick a loss function and an optimizer. So let's go down here. Our loss function, torch nn BCE loss. Let's write that in. Torch loss function equals torch nn BCE loss. Does this work? And what's our loss function? Beautiful. Okay, well, we've got a loss function ready. And you don't actually need torch here. You could just do nn.bce loss, because nn just stands for neural network in Torch, PyTorch. Well, at least I think it does. And then the optimizer is going to be torch.optim.sgd. And then we have to pass in params. So params equals model0.parameters. What is this? Well, we're going to have a look at that in a second. And the LR is going to be 0.01. So this is learning rate. And this is parameters of model to optimize. So let's just set that up. What is model parameters though? Model0.parameters. A generator. Let's get the state dict. How about that? Okay, beautiful. So this is what happens when we create, remember linear function? Y equals x. So the x is the input data. So here, our input data, the data that we created up here. This is x. And then we multiply that by a weight matrix. The weight matrix is transposed because of the way matrix multiplication works. You need things to be in the right shape. And then we add a bias. So look at what NN linear has created for us. It has created a weight matrix. And what is the size here? Well, we could count how many elements there are. 1, 2, 3, 4, 5, 6, 7, 8. Why is it that size? Well, because we've set out features to be, do we set it to be 4 or 8? Oh no, 4 times 2. And then on here, the output of this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, beautiful. So you can go through the different shapes of how these are calculated. But the point being here is that our model starts off with a random collection of weight numbers and a random collection of bias numbers. Now, the weight is the A matrix here, and the bias number is here. And when we train a model, these random numbers will get updated by the optimizer, right? By a certain, because this is the model 0 parameters. These are parameters of the model. These random numbers will get updated over time with every time our model looks at this data and goes, that first time that I predicted that line that went over there didn't do pretty well. And the next time I changed a few of these internal patterns to be a different combination of internal patterns, and then the line fit a bit better. And so I kept following that way until my loss function went down. That's a very brief overview of what it does, but essentially start with random numbers, look at the data, try to model it, update the random numbers in some way, shape or form, try to model it again. If it doesn't work, change it. If it does work, keep going. So the loss function measures how wrong your model is, so how wrong these random numbers are at predicting the patterns in this data. And then the optimizer tells, hey, you know what, model, you should try changing this 0.089 to 0.135 and see if that works better. And then it goes, okay, I'll try. And then again, the loss function will measure how wrong it is and goes, oh no, 135 wasn't too good. Now change it to 255. Oh, that's much better. Let's keep going with that. And even now, there is almost too many numbers here for humans to keep track of. So this is why we wrote code to do that for us. Because you can imagine if we're just working with a toy problem here, and we've got all these numbers on the screen going on, could you try updating all those by hand? Sure you could, but it would take you quite a long time. Now imagine if you had a bigger data set that was, say, millions of data points, or even billions these days with the scale of internet data. There is no way you could do that all by hand. So that is why we are writing code to do that updates for us. So from the top, the model that we just created starts with random numbers. It will look at the data. It will try to model it by drawing a line through it. The loss function will measure how wrong that line is. And then based on the values from the loss function, the optimizer will update the model's internal random numbers to better fit this data. And in an ideal world, we move towards a loss value of 0, which means that our model models the data perfectly. Let's keep pushing forward. So now we've got a loss function and an optimizer. What are we up to? We're up to the next exercise, number 4. Create a training and testing loop to fit the model you created in 2 to the data you created in 1. Okay, let's see what so this is where the magic's going to happen. This is the magic of machine learning, the training loop. Let's go here. And this is probably one of the things that's a little bit harder to recognize when you first come to PyTorch if you've come from another machine learning framework such as TensorFlow or scikit-learn. In scikit-learn and TensorFlow, you have a model.fit function, which takes care of all of the code that we're about to write right now. So we want to Create a training and testing loop to fit the model you created into to create it. So let's have a look at the PyTorch training steps. Training loop steps. So 1, forward pass. The model goes through all of the training data once, performing its forward calculation. Calculate the loss. The model's outputs, predictions, are compared to the ground truth and evaluated to see how wrong they are. Remember, a loss function measures how wrong your model's predictions are. Zero the gradients. Oh, we haven't heard about gradients yet. The optimizer's gradients are set to 0. They are accumulated by default, so they can be recalculated for the specific training step. Perform back propagation on the loss, computes the gradient of the loss with respect for every model parameter to be updated. This is known as back propagation, hence backwards. Step the optimizer, gradient descent. Update the parameters with requires grad equals true with respect to the loss gradients in order to improve them. Optimizer.step. So the loss function, there are 2 main functions here that we're doing, which is back propagation. I'll let you look up what that is. Back propagation, short for back propagation of errors, is an algorithm for supervised learning of artificial neural networks using gradient descent. The next one is gradient descent. Gradient descent is an iterative first-order optimization algorithm used to find a local minimum maximum of a given function. So, the loss function is what we're trying to find the minimum of. So if you imagine, let's look at these images. Yeah. Right, so imagine if we plotted our loss function to draw some sort of pattern like this. What we want to do is find the minimum point of the loss function. A curve's probably easier. Here we go. So cost, loss can be used interchangeably. Could go like a curve like that. Why do we use a curve? Well, because we can measure the gradients to go down to find a curve. Oh, sorry. We measure the gradients of a function. That's why it's a function. So there's a few steps. We actually, you know what? We're talking too much. Let's just write some code and I'll show you what I mean. So we'll talk about it while we go through. So we need to go measure some accuracy. No, we don't need that yet. So torch.manual seed. Do we use weights and biases in the course? Well, you're just going to have to wait and see. Random seed. Now we're going to go epochs. Epochs can be 100. So epochs is a term. So one epoch is look at all of the data at one hit. So if we do 100, we're going to go through 100 looks of the data. So actually, we need to send data to the device. I'll show you what happens if we don't do this. Xtrain, ytrain equals xtrain.toDevice, ytrain.toDevice, xtest, ytest equals xtest to device. So in PyTorch, computations won't work if you've got half your data on a CPU and half your data on a GPU and vice versa. All of your model and data should be on the same device. So let's just comment this out. Code and comma, welcome back. Oh, thank you. I appreciate that. Good to see me back. And then we're going to go loop through the data. So for epoch in range epochs. So that means we're just doing a for loop. So we're stepping through the data 100 times. Let's now do the training. What we're going to do here is set our model to train mode. So internally, or when you set up a model by default by subclassing nn.module, like we did up here, it's in training mode to begin with. However, there's another mode called eval mode. Eval. which turns off a few things that you don't need for training, like gradients. Why would you do that? Why would you have two modes? Isn't that just confusing? Again, this is another thing that you might not be aware of if you've come from TensorFlow or something like that with a fit function. It does this for you. It's to save compute time. So if you're just evaluating your model, you don't need to calculate gradients. So you can turn them off. So it uses less data and in turn can hopefully compute faster. So the first step, now this is a song. PyTorch, optimization, loop, song, Daniel Burke. Here we go. I need to make a video on this song. Let's sing the PyTorch optimization song together. You ready? It's train time. Do the forward pass, calculate the loss, optimize a zero grad, loss backwards, optimize a step, step, step. Let's test now. With torch no grad, do the forward pass, calculate the loss, watch it go down, down, down. Oh, that's good fun. I'm going to stand up. We need to get some grooving going with this. But this is how you're going to remember the PyTorch optimization loop, which is a training loop or a testing loop. Hold on. We're up. I think my desk just got caught on something, but that's all right. So here we go. We do the forward pass. We're going to write this up. Forward pass. So this means we pass everything through our model. Y logits. Y logits equals model 0, and then we pass it the training data. And then we go Y pred equals model 0. We need to do an activation here. Oh no, let's just see what it looks like. Print Y logits. Let's just do that actually. Before we even do a training loop, let's see what comes out of our model. Model 0 X train. Maybe we do it first 10. Have we got the classic not implemented error? Look at this. This is what absolutely astounds me sometimes when model 0 for some reason it doesn't capture the forward method because the spacing isn't correct. Has anyone ever had this to them in Collab? Look, if I copy, I don't want to copy, but I'm going to do it anyway. I'm just going to copy this. For some reason, the spacing of... You might run into this. Yeah, see? Okay, I think my return function is outside the function. Oh no. Yeah. Look at that. Tab. Tab. Have I got all my spaces correct? Not implemented error. But then if I pass it this, which is basically the exact same model, yeah, with different features, that is bizarre. Can anyone see what's going on? Maybe I need the same amount of spacing. I never get this. If I create a model from scratch in Collab, this happens so often. Super. Self. No, I shouldn't need that. Has anyone ever seen this? I'm so confused. I'm always confused when I write this in Google Colab. The spacing just seems to be off. It says not implemented error. So this is actually a good thing. You're going to get one of the most common errors in PyTorch is to have a not implemented error, aside from shape errors. And that means that the forward method is not implemented. This is very good error catching, actually. So if you ever run into a not implemented error, go back to your forward method and see what's going on here. Return this. X equals self.linear. For some reason, the indentation is here is not. Oh, maybe I need to do that. Okay, this is a good note. If you're using Collab, let me just see. What does this do? Not implemented error. This is bizarro. So right now it's saying that this method is not implemented. But if I uncomment this, this is just what I want to show you what's very confusing. And this is like a big troubleshooting step. What if I just try to copy this here? I wrote all of this from scratch. You all saw me write this from scratch. So I just want you to like realize that if you're running into these similar errors, I've run into them as well. So we're going to go through and try to fix this. Not implemented error. This is bizarre. But if I uncomment this, sorry, comment that and uncomment this, basically the same code. Except 2 layers instead of 3. It works. Oh, this one's got no. Oh, excuse me. I need to comment out this as well. Okay, so now it works. This is bizarro. Okay, so let me just talk through what the error is. So I'm going to adjust this. It's the spacings here. However, even if you create a model with the similar spacings, if you're writing a forward method on Google Colab, just keep this in mind, you may run into the not implemented error, which is what we saw before. But now we're getting a runtime error that our tensors and models need to be on the same device. So this is circle model. This is from module 02. We're going to change this back to moon model, and I'm going to readjust this to be similar to here. Now, you might be thinking, Daniel, your code above is the exact same as the code below, or it's going to be very similar, you watch. Why is it not working? Well, I don't really have a good answer for that, because I've come across this error multiple times in Google Colab when I've created a PyTorch model using a forward method and using NN module, that even though I define the forward method, PyTorch raises the not implemented error. And I've searched far and wide to try and figure that out, but I haven't been very successful. I usually go about it, figuring it out by this roundabout process that we're kind of seeing live here. So if you're running into errors non-stop, like not implemented error, please just know that you're not alone. If anyone has a fix for that, I would love to know. Let's see if all we did was copy the spacing from another model. So we just copied this code here, or something very similar to this, over to here. Not an ideal solution, but we're going to see if it works. And so far it looks like it has. Layer 3. I'm even going to remove the underscores. Just going to cancel all of this. This is actually very good error finding, because you're seeing me run into the exact same error that you may run into. And then all we need to do here is add self.layer3. And we can get rid of this. Then I'm going to change this to moon model. And let's see if this works. Oops. In features equals 2. Out features equals 1. Hidden units equals 4. Spelling mistake. Okay, there we go. And then we look at device. Cuda, model 0 static. Exactly how we had it before. Now, is this going to do a forward pass? Okay, beautiful. So now we've got a good runtime error. So just be aware that if you run into an error here when you try to do a dummy forward pass with your model and it says not implemented error, usually that's to do with the forward method not being implemented. And for some reason, if you're using Google Colab, the spacing may be off when creating your forward method, and then PyTorch will think that it's not implemented. So I've run into this error many times. I would love to have a great fix, but I don't have one at the moment, and I'm going to get rid of this. Oh no, we need the PyTorch optimization song in a second. I need to go to the bathroom. I'll be back in a sec. Okay, so why are we getting this error? Well, it's because all the tensors should be on the same device. So found at least 2 devices, CUDA and CPU. So right now our data, we haven't put that on the GPU, but we've put the model on the GPU. And we write device agnostic code by adding .to device to a lot of our data and models, because we set up at the beginning the device parameter to be CUDA if the GPU is available, and to be CPU if, which is the default, if CUDA is not available. But PyTorch doesn't automatically recognize where you want your model / data. So you use the to function or the to method to send it to the target device. So now we do a forward pass. Look at that. Oh, that is beautiful. It works now. So what is happening here? Well, we're putting some data through our model, and what it is doing, the outputs here are what we defined in the forward method. So the forward method takes X and passes it through layer 1, which is NN linear, which is if we go back up here, do we have NN linear? NN linear, which is a linear computation, does this, and then it goes through layer 2, which is the same thing but with different shapes, and then layer 3, which again is the same thing, NN linear, with different shapes, to finally it goes to the out features, which we set as 1. So now we're getting one output after it's been computed through 3 different layers for each input sample. So if we go lang xtrain and length model 0 xtrain to device. 800, 800, beautiful. So our model essentially is making one prediction per input sample. And if we just wanted to go model 0 xtrain to device, let's just do the first sample of xtrain. That's going to be its prediction, and ideally we would have wanted it to predict the label for it, which is ytrain 0 1. Jero, hello. Have I ever tried data spell? No, I haven't. I'm not sure what that is. So our model is predicting -1 for a value that we wanted to predict 1. So not very good. Now, why is it doing that? Well, because our model is still only predicting with random parameters. So what we have to do is, and by the way, a model's raw outputs are called logits. So what we have to do is convert these logits into prediction probabilities. So if we go torch.sigmoid, torch sigmoid is an activation function. Beautiful. And if we go to sigmoid, we actually recreated that sigmoid function before, but doesn't matter. We can do it again. Let me show you what sigmoid does. Where did this come from? It came from the architecture, which is, again, we cover this in section 0.2. This is just the exercises, solutions to the exercises, that is. Architecture of a classification neural network. You want the output activation is the sigmoid function. So let's look up sigmoid function for binary classification. It doesn't have anything there. Okay, some poor documentation, but that's all right. We can practice the sigmoid function. So torch a range, -100 to 100 with a step of 1. Create a range. We'll say this is A. Let's plot A. Here we go. Okay, straight line. Now, if we go plot plt.plot torch, this is what sigmoid does. Sigmoid A. Oh, it makes a curve like that. So then we got a decision boundary. So sigmoid, everything below this decision boundary, this vertical line here, gets the value of 0. And everything beyond this decision boundary gets a value of 1. Now, there's a great website I like for this, ML cheat sheet, sigmoid. Activation functions. Here we go. Sigmoid. Sigmoid takes a real value as input and outputs another value between 0 and 1. It's easy to work with because it has all the nice properties of activation functions. It's nonlinear, continuously differentiable. That means you can use it for backpropagation. What do we got? It's good for a classifier. Yeah, the output of the activation function is always going to be range 0 to 1. So this is what we're going to use to turn our model's raw logit outputs from how they looked like this into prediction probabilities. And then, because of the decision boundary, I wonder if we can plot this. plt.plot. We're just going to say everything. It's on Cuda. That's why. Can we turn this to CPU? Because it needs gradient. Okay, this is detach.numpy. Okay. Oh, maybe CPU. One more try, and then we'll just show you anyway. Whoa, that's all over the place. Okay, so what we're going to do is, instead of that jargon, is say, oh my goodness, Daniel. I hope you guys are seeing what happens when you live code. There's a lot of errors. You don't get everything right the first go. So what we're going to say with this is that everything below 0.5, which we're going to pretend that this is 0.5, this line, gets a value of 0. And everything above 0.5 gets a value of 1. So let's do this. Imagine if we had, what if this was between 0 and -1 and 1? Or 0 and 1, and it was 0.01. Okay. This is cool. Okay, there we go. So let's see this. What if we do torch round? We need to get them. What does our Y train look like up to? We need to get our. What we're trying to do is get our model's predictions in the same format as our model's labels, or as our data's labels. So we need to convert these. So Y logits. So logits print is the raw outputs of the model. Raw outputs of model. Whoa, Alex, you got your first job in machine learning. Congrats, my friend. And then we go prediction, probabilities. Pred probs is torch.sigmoid. We use an activation function on the logits. And then finally, we go from prediction probabilities to pred labels by rounding the outputs of the sigmoid function. Torch.round. There we go. Okay, beautiful. So these are all crap at the moment because our model hasn't learned anything. So our model raw outputs. Let's do this. Model raw outputs are logits. And our loss function, we used BCE loss, but we could also use, this is another confusing thing about PyTorch, loss function equals nn.bce with logits loss. So if we look at the documentation for these two, BCE with logits loss, which one should you use? Well, it actually says they do the same thing, except the BCE with logits loss has a sigmoid layer built in, so we don't need to pass it logits that have gone through a sigmoid layer. We could just pass it raw logits, hence with logits loss. Remember, logits are the raw outputs of our model. It says it's more numerically stable. By combining the operations into one layer, we take advantage of the log sum exp trick, I'm not sure what that is, for numerical stability. So generally, PyTorch recommend using this for more numerical stability. So what does this look like? Let's do that. Y logits equals the forward pass, and then let's go Y pred probs equals torch.sigmoid on Y pred probs, on Y logits, and then Y pred equals torch.round on Y pred probs. So that's the forward pass. 2, calculate the loss. I'm going to just get rid of this. Get rid of this. And then the loss equals loss fn, and we're going to pass it in y logits compared to what? Y train. So let's write this down. Loss equals compare model raw outputs to desired model outputs. Then we can also calculate the accuracy here. Let's see if we can do that. So we can go pip q install torch metrics, and then from torch metrics import accuracy, and then accfn equals accuracy dot to device. So torch metrics is, we could code our own accuracy function by scratch, but let's look this up. Torch metrics is a great library that's based on PyTorch. Yeah, there we go. Which calculates different metrics in a very PyTorch or PyTorchy way. So we could code our own accuracy function from scratch, or we could just import that. So let's write that down. Hey Siri, stop the timer. My timer's going off because I've done 2 hours of coding this morning. That's exciting. Let's calculate the accuracy. I try to start every morning with 2 hours of coding. So we're just going to, we have to install torch metrics because Collab doesn't come with torch metrics. So we've got accuracy, and then we can calculate the accuracy by going accfn, but we need to put in ypred and ytrain. So the accuracy function needs to compare pred labels with actual labels, and we'll put here not logits. So then what do we do next? What's the PyTorch optimization loop song? Well, 0 the gradients. Optimizer 0 grad. And then we have next, we need to do loss backwards. So this is back propagation over the loss. Loss backwards. And then we're going to go step the optimizer. So perform back propagation. So if you want to look into what's happening here, I'll discuss this in reverse order. So I'll go loss backwards first. So this is back propagation. Backward propagation of errors is an algorithm for supervised learning of artificial neural networks using gradient descent. It's going to calculate the gradient function over our over all the parameters in our model. So with respect to the loss, and then the optimizer is going to perform gradient descent on those gradients. So that's where these two things come in. So I'm going to go here, back propagation. There, and then if you want gradient descent, gradient descent there. Beautiful. And so this is where the optimization loop song comes in. We've done the training. So, PyTorch optimization song. You ready for it? It's train time. We do the forward pass, calculate the loss, optimize a 0 grad, loss backwards, step the optimizer. No, optimize a step, 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 I don't know the full song yet. I promise by the time the course comes out, I'll know the song off by heart. I should make a video just about this song. Why do we zero the gradients? Well, when we do this step, because every loop, it's going to add those steps up, but we want it to reset itself every time, so it only does a little bit of adjustment. Why does it do this? Well, there's a lot of internal things that PyTorch does behind the scenes to optimize our code for us, perform automatic gradient calculation, which is called autograd. So that's the backwards propagation, so calculate the gradients with respect to the loss. It adds them up every step in the loop. So we want to, or every time it steps. So we want to, instead of it accumulating them, instead of like say 0, after iteration 0, they're 10. After iteration 1, they're 20. After iteration 1, they're 30. We wanted every iteration to start at 0. So after iteration 1, it's up here. And then it gets zeroed, and then it goes back to here. And then zeroed, back to here. So that's what happens with optimizer 0 grad. But just remember the PyTorch optimization song. It's train time. Do the forward pass, calculate the loss, optimize a 0 grad, loss backwards, optimize a step, step, step. And now let's test. I need to update the song because there's a better way with torch.inference mode. So when we're doing testing, we're getting our model to make predictions using the patterns that it's learned in the training loop on the testing data. And so that's why we use model.eval, and with torch.inference mode, both of these together kind of tells PyTorch, hey, a lot of the things that you turned on for training a model, such as automatic gradient calculation, we don't need that during prediction, during inference. We're not calculating gradients when we're evaluating our model. We just want to do a forward pass, aka the song. Let's test now with torch no grad. You might see this as well, torch no grad in some places, which means no gradients, no gradient calculations, which is used in gradient descent and back propagation. The new one is inference mode. So this is the faster way of doing things. I would recommend using this. This is what PyTorch recommends at the time of recording this. And to do this, we just want to do a forward pass with our model. Forward pass. So test logits. Remember the raw outputs from our model are just the logits. So we go model 0 equals model 0. But this time we're going to do the forward pass on the test data. And then we can turn it into test preds by going torch.round, torch.sigmoid, and then we will use test logits there, and then we can go to calculate the loss / accuracy, and then we go test loss equals loss fn. Remember our loss function, which is binary or BCE with logits loss, wants the logits as input plus the testing labels this time. And then for the test accuracy, we can use our accuracy function, which is going to take in test pred and our y test labels. And then our exercise says we have to, what do we want? Print out the progress every 10 epochs. So let's do so. Print out what's happening. Hey Abdullah, you recently took my ML course in Udemy. Here to say hi. Well, thank you for joining in. So if epoch, because we're looping through epochs, we can go, let's count the epoch here. If epoch divided by 10 equals 0, let's do a print statement of f epoch is epoch, and then we'll go loss equals loss, and then we'll go acc equals accuracy, and then we can go test loss is test loss, and test ac is test ac. But we probably want these as 0 to f, just to 2 decimal points. That should be enough. Let's see if this works. We definitely have an error somewhere. Expected all tenses. So this is, I said before, we're going to run into an error. Why? Because we haven't got the data on the same device as our model. So what happens? Let's just familiarize ourselves with this error. Expected all tenses to be on the same device, but found at least 2 devices. Cuda. So our model is on the GPU, and our data is on the CPU. But what happens when we put our data to the GPU as well? Oh, we got something wrong here. Using a target size torch 800 that is different to the input size torch. Oh. Please ensure they have the same size. So we've got something going on. We need to, I just want to show you print y logits. We need to squeeze our outputs. I want the shape. So see how we have this extra dimension here? Oh my gosh, that was just 800 outputs. I could have just gone up to here. We want to remove this extra dimension. So watch this. If I go dot squeeze. Oh, did it remove anything? Oh no, I need to squeeze the end of it. Dot squeeze. Watch this. It's got a bracket here. This is what we have to do. We have to remove that extra dimension. There we go. And then if we do the same here, watch this. Bracket there, bracket there. We're going to get rid of that by squeezing it. Squeeze just means to remove all the 1 dimensions. There we go. Beautiful. And then if we put squeeze here, magic. Okay. So what we have to do is just squeeze the output of this. And remember what it looked like before? Squeeze. We might only print out the first 5 every time. That's what it looked like before. We run it again. Cuda error. That's all right. But look at this. Beautiful. We squeezed it. Device side assert triggered. Cuda kernel errors might have asynchronously reported at some other API call. Okay, so I feel like this is because we have already put our... We've done a few different things here, so we're going to just reinstantiate everything. Because our code is a bit jumbled. What I'll do is I'll just delete a few extra things and write this. Write that. Oh, we've got a CUDA. We've got an actual CUDA error. This is excellent. I'm going to just restart the runtime here. Rather than troubleshoot a CUDA error in this video, let's just run all before. See if this works. Oh, we probably need to squeeze this as well. The target has to be an integer tensor. Are you kidding me? Oh, torch metrics. Y pred. Just going to turn this into an int. Oh, this is lost backward instead of backwards. Okay, we're getting typo errors galore here, but this is excellent. This is excellent. This is the things you're going to run into when you do this stuff. Oh my goodness, what have we got wrong here? Oh, we need test logits, not Y logits. Is this going to work? It's working, but it's not learning. Oh no, that's okay. Our model is predicting at about 50%. But let's plot the predictions and see what happens. We've got a plot predictions function in here. No, plot decision boundary. Here we go. Let's bring this in. Plot the model predictions. Bring that function in. And then we can go in here. Plot the decision boundary. Look what's happened. This is why our model is getting 50%. Because it is trying to divide our training and test data into red and blue using straight lines. So how do we fix this? Well, we have to go back up to our model definition and we have to add in some nonlinearity. So if we do relu here, equals nn.relu. So remember what the relu function does. Relu. There we go. So the relu function, it turns everything that's negative into 0 and leaves everything as positive as positive. So if we just add in this simple nonlinear function to in between different layers of our model, self.relu here, and then we're going to go self.relu here. Let's see what happens. Oh, we still don't get too good, but we got a little bit better than what we did before. Okay, how about we increase? I think we're going to decrease this, decrease the learning rate, and we're going to up the hidden units to 10. Sorry, increase the learning rate to try to get our model to learn faster, and increase the number of hidden units. Oh, there we go. Beautiful. So what did we do just then? We increased the learning rate to get our model to learn faster, and we increased the number of hidden units in our model to learn more features of the data. And now what do you think will happen if we train it for longer? So 1,000 epochs instead of 100 epochs. So now not only do we want our model to learn faster by increasing the learning rate from 0.01 to 0.1, we want to train for more epochs, so giving our model more chances to look at the data. So an epoch, remember, is one forward pass of the data. And we're increasing the number of hidden units. Where's the TensorFlow playground? TensorFlow playground. Inside our model to go from 4 hidden units per layer. Well, this doesn't even go up to 10. Now it goes to 10. So let's see what happens. We'll train it for 1,000 epochs. Oh my goodness. Oh my goodness. Look at that. Now we have a test accuracy of 1.0 and a training accuracy of 1.0. So what happens if we plot our predictions again? What does it look like? Hey, beautiful. Look at that. So that is, we introduced the power of nonlinearity and we upgraded our model's potential to learn. And so we went from drawing just a straight line and we added just one function to our model, which was the ReLU function, the nonlinear activation, the ReLU function. We put that in here, and then our model went from only being able to draw straight lines to being able to draw non-straight lines as well. And we can replicate that on here. So if we go linear, let's turn this down to 4. So we've got 2 circles here. If we just use a linear activation function with a learning rate of 0.1, what's going to happen? Well, the loss is about 50%. So 0.5, roughly about 50%. Why is that? Well, if you're working with the binary classification problem and your accuracy or your loss is around 50%, it means your model's basically guessing, because you could randomly go, okay, this point is a blue point, this point's an orange point, or just predict them all to be orange points, and you would get about 50-50 if your class samples are balanced. But what happens if we stop this? What happens if we just change this from linear, we add in a ReLU function, just like we did here? All we did was we added in a ReLU function. You ready to watch this? Oh my goodness. Have a go at that. Our test loss just went from 0.5 to 100 times less. More than 100 times less. It's modeling the data perfectly here. All right, and we've got 2 features, very similar to what we're working with. 4 hidden neurons. Learning rate of 0.01. I'm not sure what optimizer they're using here. But we've also used the same ReLU activation function. How beautiful is that? That's the power of neural networks. A combination of linear and non-linear activation functions. So that took us a while to build a training loop. But what you may have noticed is we've got a lot of boilerplate code here. So you could functionize this into a function such as def train model. And then it takes as a model as input, a loss function as input, an evaluation function as input, and an optimizer. And then it just does these steps. Then you could have a def test function, which does these steps. And then you could have a def train function, which combines the train step and the test step functions, which then outputs how the model is doing. So there's a lot of code here that we could fix up. But what I might do is just go from the top. I think if we train from 1,000 epochs from scratch, it should just work. We'll print out only every 100 epochs. There we go. Okay, so by changing a few parameters, we go from after 100 epochs, 50% accuracy, to 76%, and then all the way up to 100% accuracy, and now we can plot our model predictions. How good is that? So we're working through the exercises here. We're now up to, we've done number 5. Oops. And now we're up to number 6. So replicate the 10H function in pure PyTorch. Okay, so we saw how to do. So we've got some different activation functions here. We use the ReLU function, but what does ReLU do behind the scenes? Remember, ReLU for your model's parameters turns the negative parameters into 0, and the positive parameters, it leaves them as is. So it creates nonlinearity in that sense. The 10H is another form of nonlinear activation function. Oh, we got a bit wonky here, but it still works pretty good. So let's replicate that, what it looks like in code. But if we go torch 10H, so PyTorch have a lot of inbuilt nonlinear activation functions. So what we're going to do is we're going to replicate this. Instead of using torch 10H, so let's just create this. We'll go, what can we call our tensor? We'll go G. We'll go tensor A equals torch, A range, 0 to 100. Oh no, we'll go negative 100 to 101. And then let's go torch, we'll go PLT dot plot tensor A, just to visualize it. And then we'll go plot PLT dot plot torch dot tanh tensor A. So we get a similar output to the sigmoid function, but now we're going to replicate this with without using torch.tanh. So let's write this def tanh. It's going to take as input x, and it's going to return something. So we want to create a function that replicates this functionality. So now let's go ML cheat sheet tanh. Let's look up the formula for this. Tanh z, which is logits, z is another thing for logits or input, equals exponential to the power of z minus exponential to the power of negative z, on top of exponential z plus exponential to the power of negative z. So let's replicate this. We want torch exp, which stands for exponential, exp on x minus torch dot exp. Let's write this down actually. Source exp on negative x, and then this is going to be over torch.exp over x plus torch.exp or exponential to the power of negative x. And they use z in this example, but I'm just using x as the input. Now let's see if this works how we want it to work. Tanh tensor A. Beautiful. How cool is that? We just replicated a nonlinear activation function, and you can do the same for many more if you just go torch activation functions over here. Nonlinear activation. So some of the most simple and most common ones are going to be ReLU. There's different forms of ReLU like CeLU, CeLU, GeLU, Sigmoid. We've seen Sigmoid. Mish. There's lots of them. Tanh, glue. So go check these out. You're going to see a lot of them in practice. ReLU is probably the most common because it's the most simplest. That's another thing you got to keep in mind is when you're implementing different things is simplicity usually wins if you want to deploy your models into applications. So just keep that in mind. Now we're going to put everything together by creating a multi-class data set. So let's put everything together. So construct a model capable of fitting the data. Create a multi-class data set using the spirals data creation function from CS231N. This is this code here. So this is going to create a spirals data set. Just using very similar code to what we've used before. I need to write down here as well. Let me just say, split the data into training and test sets. 80% train, 20% test, as well as turn it into tensors. PyTorch tensors. Okay. Let's now copy this. We've got a few steps here, but basically all we're going to do is turn everything that we've done so far, put together everything we've done so far into a multi-class classification problem. There's a fair few steps here, but that's all right. So create a multi-class data set. Let's just see if we can do this on our own. So this is using the spiral data set. So I wonder if I want to change the colors of this. Red, yellow, blue. I want to change these to red, yellow, blue. Is it BU for blue? Okay, wonderful. So we need to, now we have, or before, let's check what we had before. We had two classes. So we had binary classification, red dots and blue dots. Now we have three classes, blue, yellow, and red dots. So this is using some code from CS. I've linked the reference here. CS231N. That's a great course on the in-depth, behind-the-scenes stuff, what's going on neural networks. We're focusing on code here. So let's see what the length of X is. Okay, beautiful. And length of Y. Let's create train and test splits. So X train, X test, Y train, Y test equals train test split. We'll just import. I'll show you where we get train test split from. Train test split on X, Y test size equals 0.2, and the random state can be random seed. Wonderful. I'm just going to set up a random seed here. (42) MP random seed. Wonderful. And now we should have length X train, X test, and we'll check length of Y train. Beautiful. Okay. So now we have 240 training samples to and 60 testing samples. So now we want to, I think we can turn the data into tensors first, actually. Or we can just do this. Turn the data into tensors. And we're going to pass in X train. The D type can be torch.float. Data is into tensors. Okay, and then what was the next step? So we split it in to training and test. Construct a model capable of fitting the data. You may need a combination of linear and non-linear layers. So let's create a model. Why don't we use the sequential API this time? Fitting the data. So model 1 equals. Now, the sequential API is quite a bit simpler than the NN module, but sequential is subclass of NN module. So before, when we created a model, we used this, NN module. I'm just going to delete this so it's a little bit less code. We did all this stuff, but in the end, our model just went through a straightforward stack of layers. Like there wasn't anything too complex in our forward function. It just went, hey, go through layer 1, then a relu, go through layer 2, then a relu, go through layer 3, and then you're done. How about we do a little bit different this time? When we go nn.linear in features, we'll hard code it this time. The benefit of creating a model class is that it's more flexible. Such as before, we could set the in features. The benefit of NN sequential is that it's just more straightforward. So you can use them interchangeably. Like you could use an NN sequential inside a subclass of NN module. So let's go this out features equals 10. So that means our first layer of our model is going to take in 2 features, which is what X has. Zero, zero. And then it's going to output 10 features. And then our next layer has to take in 10 features because our first layer outputs 10 features. And then we're going to get it to out 10 as well. And then NN linear, our final layer, is going to take in 10 features from the previous layer. And then it's going to output how many? Well, let's have a look at Y. First 10 of Y. We have 0, 0, 0, 0. Oh, wow. How about we look at Y train? So we have 0, 2, or 1. So we have 3 different features. So 3 different labels. Or in this case, 3 different classes for 3 different colors. We have yellow, blue, red. Oh, sorry, yellow, red, blue. And that is why we need our model to output 3 features, 1 for each class that we have. And so if we send this to device, oh wait, what are we missing here? We've only got 3 linear layers. So will our model, using just straight lines, just linear layers, be able to model this data? I don't think so. We need some non-linearity. So let's bring in relu. We're going to intersperse relu in between each of the 2 middle layers. Now, there's actually really no set in stone way of how you can interlace these layers. However, you'll see quite often that if you do a linear transformation, so a linear layer, you'll quite often see straight after that some kind of non-linear transformation, so a non-linear activation function. So linear layer, non-linear layer, linear layer, non-linear layer. Linear layer is the output. Could have an activation layer here too. Such as in the case, we might want our model to output prediction probabilities instead of logits. So why NN softmax? Because if we look at the architecture for a classification model, if you have more than one class, where is it? Architecture. If you're working on multi-class classification, which we are, the output activation function, we saw that before, to go from logits for binary classification to prediction probabilities, we use Torch Sigmoid. But now, for multi-class classification, to go from logits to prediction probabilities, we want to use softmax. So we've just created our model. Let's get rid of that. And let's see what happens when we do model 1 on xtrain. What happens? Let's get the first 10. Oh, again. All tensors need to be on the same device. Goodness gracious me. We need some device agnostic code. Set up data to be device agnostic. So we need, let's just set this up here. We don't need to do this again, but we're going to do it anyway. Prepare device agnostic code, just to remind ourselves. Device equals Cuda if torch.cuda is available, else CPU. So the model's going to go to the whatever device is available. And then we want the same for our data. Xtrain, Ytrain equals Xtrain to device, Ytrain to device. We'll put our training data there. Then we can do the same for Xtest. Xtest, Ytest equals Xtest to device, Ytest to device. And then we're going to see what our forward pass looks like. Wonderful. We get one logit value per class that we have. So this is a sample here. And we get one value for class 0. We get one value for class 1. We get one value for class 2. So let's do this. So print out model outputs. So this is print logits. And then we'll go print. But what if we squeeze these as well? Oh, we don't need to squeeze those actually. Or do we? Same thing. And then we want print pred probs. If we want to go from logits to pred probs for a multi-class classification, we need an output activation of softmax. So torch softmax on model 1 xtrain, and let's have a look at the first 10. Oh, goodness gracious me. We have to tell it, Sigmoid, that we want the softmax to go on the first dimension. Wonderful. Now we have prediction probabilities for each class. Now, with the prediction probability after using the softmax function, because each one of these samples is now going to add to 1. So if you add it up, 0.3976 and 0.2210 and 0.3813, you will get 1 or very close to. And the one that the class that the model thinks is most likely that the particular sample is associated to, in our case, blue, yellow, or red, or 0, 1, 2, is going to be the indexed value here with the highest value. So in this case, index 0 has the highest value compared to the rest. Index 2 is quite close. So for this particular sample, the model thinks that the most likely class, red, yellow, or blue, is the first one, index 0. And then I think it's a similar pattern for the rest of these samples. But again, remember, this is using an untrained model. Print out untrained model outputs. So they're basically gibberish right now. Our model doesn't have very much predictive power. And so now we want pred labels. To get the pred labels, we can take the argmax across the first dimension as well. So let's see what that does. Wonderful. So now our pred labels are in the same format as our ground truth labels. So Ytrain, and of course it's going to get the first 10 basically wrong, probably going to operate around 30% accuracy because it's just guessing. And if the model just guesses 0 for every class, because we have 3 balanced classes, we have equal points between blue, yellow, and red, it's going to default to around 30-33% accuracy. But now, let's construct a training loop. What's our song? Build a training loop for the model. What does it say here? What was the instructions to do? Oh, we forgot one thing. We need to build the loss function and the optimizer capable of handling multi-class data. Optimal extension, use the Atom optimizer instead of SGD. Okay, beautiful. Let's do that. So we want to set up loss function and optimizer. So loss function is going to be nn.cross entropy loss. Why is that? Well, for here, if we're doing binary classification, we use binary cross entropy. And if we are doing multi-class classification, we use cross entropy. So cross entropy without the binary. And that is torch.nn.cross entropy loss. And for the optimizer, this time we use SGD before, stochastic gradient descent. This time we're going to use the atom optimizer, which is possibly the most common aside from, and we need it to optimize our model 1 parameters. And we'll set the learning rate to maybe 0.001. Atom is pretty good with a lower learning rate. So again, the two most common optimizers are SGD and Atom, but there are many other variants of optimizers, just as there are many other variants of loss functions. Which one you use will be depending on the problem. Most often for binary and multi-class classification, you'll look at a setup similar to this. So now let's build the training loop for the model. Epochs equals how many? How many did we say for the exercise? It needs to reach over 95% testing accuracy. So let's do it for 1,000. And here's where we can do our training loop song. So loop over data. So for epoch in range epochs, we're going to do our training loop song. So do you remember? It's do the forward pass, calculate the loss, optimizer, 0 grad, and then we're going to do loss backwards, and then we're going to go optimizer, step, step, step. So there's our song. We do the forward pass, calculate the loss, optimize a 0 grad, loss backwards, optimize a step, step, step. And that's the training loop optimization song. So training, we're going to go model1.train, and then we're going to do the forward pass. So we're going to go y logits, because remember the raw outputs of our model without any activation function applied are called the logits. You can look up what the logits mean. I don't actually really know. I just know that that's the name of them, and I like to interact with the code rather than sort of dig into the names of different things. I think it stands for log something, log probability or something like that. And we're going to pass it the training data. And then we're going to, because we've already set, we could set the data again to the device, but we've already done that up here. And then we can calculate the ypred equals, what does that equal? Well, we need to go torch softmax across the logits and across the first dimension, and then we need to take the argmax also across the first dimension, because we turn the logits into prediction probabilities using softmax, and then we find the prediction classes, the prediction labels, by taking the argmax. So the highest prediction probability value, or the index where that prediction probability value occurs. So then number 2, we need to calculate the loss. So the loss equals loss function. We're going to pass it in the logits, and we are also going to pass it in ytrain, the labels. And we can do the accuracy as well. So let's go, we'll get the accuracy function that we got up before. I'll bring this down here. Accuracy function, acc equals and then we're going to do optimize a 0 grad, 0 the gradients, because by default they accumulate. We'll take the loss backwards, we'll perform back propagation over the loss, and then we're going to go optimizer. We're going to step the optimizer and figure out how to improve our model's parameters with respect to how we best improve the loss. So there's a training loop. Oh, have we instantiated that? And then we can do testing. Testing is model1.eval, and then we can do torch.inference mode for making predictions. Remember, when you're testing, you can just you don't need to calculate gradients or anything like that. So these 3 steps aren't required for testing. So testing is also just making inference and predictions. We're evaluating our model, hence why we turn it to eval mode, model 1 eval. We turn on inference mode, which means we're making inference with our model. And then we go test logits equals model 1. We'll pass it the test data. And then we'll go test pred equals torch.softmax. And we're going to get the softmax across the test logits, the first dimension. And then we're going to take the argmax also across the first dimension to get the test labels. And that's the forward pass. Forward pass. And then 2, we're going to calculate loss and accuracy. So test loss equals loss fn on test logits and test pred. And then finally, we're going to get the test ac, which equals acfn on test pred. Oops. We want that. Test pred and y test. I think it'll be the same regardless of the order that we put that. And then we'll print out, so if epoch divide by 10 equal, oh no, divide every 100 epochs. Let's do that. What's going on here? Why is this wrong? If epoch divided by 100 equals 0, let's print out what's happening. So print, and then we want f epoch, and then we want loss equals loss, and we're going to take that to 2 decimal places, and then we want ac. I'm going to go ac to 2 decimal places, and then we're going to go test loss, which is test loss to 2 decimal places, and we're going to go test ac, which is test ac to 2 decimal places. Wonderful. Now you reckon this is going to work? Let's find out. If in doubt, run the code. Oh, we got something wrong here. Loss function not implemented for float. Okay. What if we just pass in the straight up preds here? Oh. Expected to be in range of -1 to 0, but got 1. Oh, let's print out our preds. Print y pred. Troubleshooting on the fly here, team. 0, 0, 0, 0. Huh. What's y train look like? Do we need this as floats? And do we have cross entropy loss? Let's look up this. Torch cross entropy loss. What's happening here? Input target. Yeah, what gives here? Why are you not working on the logits? Not implemented for float. Huh. So that comes out correctly. What if I turn this into torch tensor? D type equals torch. Not implemented for int. But also not implemented for float. Now, this is another error that you're going to run into quite often. Runtime error, NN loss forward, not implemented for float. But if we go here, they're all floats, yes. And then if we go like this, they come out as integers. So what if we put in ypred here? ypred.unsqueeze. Host softmax not implemented for long. This is good troubleshooting right here. What if we unsqueeze on dimension 1? Let's Google this and see what comes up. I've never got these errors. That means I need to have the dimension of the outputs tensor 1, 2. From the docs, I'm assuming your C equals 2 and N equals 2. Pseudo maze, what's happening? Why is this not? We're doing some exercises for my upcoming PyTorch course, but we're running into some errors, which is actually quite good. So the model is outputting. Why on earth? What D type is this? Float 32. Okay. This is not making sense to me. You're telling me torch float 32. So they're both in float 32. So this is the way we should be looking at. Oh, that's that one of those. I've never seen this error before. And then loss forward, reduce CUDA kernel 2D index not implemented for float. What about ypred? And we got the same. So this is another strange error I haven't really faced before. We're looking at our shapes are the same size, but now we're getting dimension out of range, expected to be in range of -1 to 0, but got 1. Pulling out all the tricks in the book here. Host softmax not implemented for. Oh my goodness. This is an absolute crack up. Well, lucky I went through troubleshooting all of this before putting it out as some exercises. Live demos, you're right. But so the shapes are right. The function looks like it's being used correctly. Cross entropy loss. Oh. How does this look any different? See, this is what you can do. You can come to the, if you're having trouble with things, come to the, this is a great lesson actually. Come to the PyTorch documentation, see what the example does, and copy it. So let's have a look at the input and the target. What if I did that? Not implemented for float. These are floats. I don't get it. They're float 32s. Let's see if I can solve it using my own code. Loss function. Adam. This is exactly what this looks like. Wonder if I change this to wonder if torch. Ah. Nope. See, this works. Wonder if this code still works. I'm going to try and fix this, you know, because this is what people are going to run into as errors. This is a really recent error. In my case, the custom target I was comparing to the model. D-type errors, friends. You're going to run into them all the time. They're both float 32. Not implemented for float. Am I resetting Y train somewhere up here? All float 32. See, this is code, exact same code I wrote that works for a slightly different data set. Output. So then Y logits equals model 1 X train. And then if I change this to pred, I'm seriously a bit stuck here. I have no idea why this. To me, it should be working. Convert PyTorch dtype. Torch.tensor. Then we're back to where we started, not implemented for float. Not implemented for float. Maybe I'm using a version of PyTorch that's got an error. No. I'm going to try rebuild the model with NN module and see what happens. Why do you do that, Collab? You don't need to delete my code, my friend. Come on, Mark. Come on, Mark. Now, this is where some reason, if it doesn't work on the forward method, we want... What's it got going on here? Why is it output to int64? absolutely perplexed. I need to restart the runtime. What if I turn this into an int? Now it's not implemented for int. Not implemented for float. What form should the labels be in? This is... Friends, I actually don't know. Oh, is it a long tensor that's not working? Oh my goodness gracious me. So now I've changed it to a long 64. Oh my gosh, it worked. Okay, so we needed our labels as a long tensor. So this is the example. What did that take? Like half an hour, maybe longer, of troubleshooting of labels need to be of type long. But I'm glad I recorded this video because now you can see how long it took me to actually troubleshoot an error like that. I'll never forget that again, will I? Oh, lost backward, not backwards. Oh my gosh, it's working. Stop, stop, stop. Stop, man. Stop. After heroic effort, troubleshooting, we got there in the end, friends. It was one of the errors that I actually would have not thought for a long time would it have been. But that's all right. The error is always the last place you look. How's our model going? Oh, slowly getting better. Oh, I think if we up the learning rate a bit, it'll get better quicker. There we go. Okay. Our model is performing excellently. Yep, with the atom learning rate up. Now, let's go plot. We can get our code from above here. Hey, there we go. Woohoo! Would you look at that? Our model is predicting pretty darn well. So, with that being said, we are now through all of the exercises that come with notebook number 2. It took us nearly 3 hours, so that's actually pretty good. With a fair bit of troubleshooting. We got over 95% accuracy, and we plotted the decision boundary. So if you'd like to see all of the code for this, it'll be on learnpytorch.io, and the exercises and solutions will be on the GitHub as well. So it's Mr. Dberg/PyTorch Deep Learning. The default notebooks will be here in the main repo, and then the solutions and exercises. So we just went through number 2. Not there yet, but I'll add them there in a second. I might just add them there. I'll tidy them up and I'll add them into the solutions folder as well. But if you want more, check out PyTorch, learnpytorch.io, and I'll be back in an upcoming stream. We'll go through more PyTorch, but this is a pretty good overall introduction to a PyTorch workflow for classification on a couple of toy data sets, and we had the bonus of running into a fair few errors that you'll often come into in PyTorch, namely the forward not implemented error. So if you get not implemented error, check out your forward method, and a whole bunch of data type / shape calculations errors when calculating the loss, oftentimes, and devices. So oftentimes when you get errors in calculations, they'll either be shape errors, data type errors, or device errors. And we saw all of those in here. So thank you so much for tuning in. I will see you in an upcoming stream where we will tackle more errors. Peace. Thanks for tuning in, Ajax on. I appreciate it. See you later, my friend.